Okay, starting the stream up. I'm just double checking our sound, the video. Let's see how it goes. So I'll unmute in a second. It says we have an excellent connection. All right, I do hear myself. It seems pretty good, at least from my own. Yeah, I don't have a ton, like I'm not maxing out the volume or anything. I wanted to take a look at like customer wait time for this homework number 5. So this is our data-driven decisions. We've done a few different homework assignments. This is our last real like assigned thing where I think it's an interesting study into how uncertainty really plays out. And there's 2 parts to this. One, uncertainty in the process, like we folded paper airplanes a number of times. We got a bunch of data, and let's see if this is all. Yeah, so we had 2-handed data, 1-handed data. They both had different means. They both had different standard deviations. There's overlap in like how things were assembled. Like half of the data for 2 hands is representing like, let's see, less than 55 seconds. Meanwhile, the only, or let's see, 40, so let's do this. 40% of our 2-handed like folding times were 50 seconds. But meanwhile, for that one-handed model, there were only like 18 to 20% of our times that were less than 50 seconds. So a definite difference in both the average, so this 50% line, and the standard deviation, so like the spread of the data, because the steeper this curve is for our cumulative distribution, the more, like in one case, there might be, if the standard deviation was 0, that we measured 100 times and they were all 50 seconds, then this would be a 0 and then a straight line up to 100% and then a straight line over here. It would look like a step function. So the closer this thing gets to a step function, the smaller that standard deviation is. So the bigger the slope, the more variability in our data. So we have that, and I'm gonna come up here and grab my time 2-hand and paste it into my homework 5 work. I'm gonna make a new thing there. No, I'm trying to get back to here because I also want this time 1-hand. Copy that, paste it in here. So run this. And what I want to do here is for now I'll look at 1,000 different assemblies. So what this is saying is not that I'm going to assemble them for the next 1,000, like I'm not going to do 1,000 in a row, but just imagining like showing up to work every day and we just have people assembling these parts. I'm trying to get a sense of like if there's bigger variation in our process time, what does that do to our customers that are showing up at random intervals? Because if we have just as likely of a chance of a 10-second assembly as a 100-second assembly, there's a bigger chance that customers will walk in during 100-second assembly versus 10 seconds. So it would almost be better to extend the time. If we come back to these plots, at least for consistency, it would almost be better if this looked like if both of these were just flat lines and then 150, and we could tell people whenever you show up, you'll always wait for 150 seconds, and or we might tell them 200 and then always give it to them 50 seconds earlier, rather than like pell-mell just sort of randomly getting stuff out the door. So some people wait a long time, other people sometimes get it quick. But all right, so I'll use 1,000 assemblies. My average part time, that I'm going to use this 2-hand time to start. 2-hand. Wait, time 2-hand? Oh yeah, that's why. Time, thank you. And there we go. That's what I want. Time 2-hand mean. No, dot. I'm still trying to figure out how to use the AI, because sometimes I hit tab and then it works, other times it doesn't work. So that's going to be my average part time. The standard deviation of my part time, that's what I want to use here, this time 2-hand. I think tab works. Okay, tab is the way to go. So when AI is telling you, hey, are you trying to use this? Hit tab and then it'll pop it in there. So I have my data. I'm taking the average and I'm taking the mean. I'm just going to turn that into a normal distribution. And once I have a normal distribution, I can generate random numbers, as many as I want and as many times as I want. So I'm using this default random number generator to say, all right, take that part ready, and I'll show the results to start. Oh, part ready. Maybe I should run things in order rather than editing and not running. All right. Oh, and we gotta get rid of, we have some times 60. I want to get rid of this. Just leave it all in seconds, because I think everything's in seconds. So let's try that again. All right. Right now, there are times, because I have an average of 60 and 3 standard deviations is now going to be negative time. There are times when I'm saying it took negative time because of the way, because I'm saying that parts are being created on average every so many spots. So instead of that, what I'll do is rearrange them to say part ready equals sort part ready. So I'm going to sort the data and then look at the differences. So there's any of those times that were really small, they end up being like small time steps like that. We can create more bins if we want. So so we have a lot of really short ones now, and then all these other ones that are a little longer. And I don't need that times 60 in here. But I do want to change this to like 300. I'm just extending these horizontal lines. They're just guiding lines for my analysis of 25, 50, and 75%, and then 100%. Let's try that. So there are like 10% happen very quickly just based on how things are going, and then 50%, this 50% line is less than 50 seconds. Just based on what I generated so far. So now I'll have 100 people all arrive. They're going to come at random times during the assembly process. So they'll just show up, and sometimes they'll be in this short time period, other times they'll be in this long time period. And I'm trying to figure out how long is this person waiting. And I gotta get rid of these like times 60 stuff. And I'm gonna extend this out to 300 seconds again. So when people are showing up randomly, what I'm seeing is that half of the times that I measured were kind of 25 to 30 seconds. So if I'm telling people, all right, it'll be less than a minute, meanwhile, most of the people that showed up were in at least like more than half or around half, 50%. So 50% had 130-second wait time. Like they're waiting twice as long as what I had said because that standard deviation is so large. And this is kind of what we're looking for in this analysis, is what is the difference between our measured times and then when people actually show up. Because the chances that someone showed up in a 1 second time interval, we can see is almost nothing. Like nobody shows up during that one tiny little second, so they're going to be waiting for these parts for longer times. But the chance that someone shows up in that 300-second interval is much bigger. Let's see. I would have expected it to go to 100% at some point, but I'm just trying to see if I missed anything along the way. All right, so let's go back up. Instead of time 2 hand, I'll try time 1 hand. And try time 1 hand again. So now my histogram looks different. There's less of these like small times because there weren't as many of those like negative times that were happening. And when I look here, now I have this curve. My 50% line is now up here around a minute and a half, like this 100 second. It still says minutes between parts. I guess I should change that, right? Seconds between parts. So then I'll generate 500 more people and tell them to arrive at random times. Now I'm seeing that because I don't have as many like short times, it's a little closer. Like if I had said that it will be 100 seconds, again, let's change that to seconds. If I had said 100 seconds, it's not too far off. It's more like 120 seconds. So here it would make more sense to tell people like, hey, it'll be 2.5 minutes in between. Like when you show up, it'll be about 2.5 minutes till your part's ready, and that's a better indicator for at least half of our customers that are coming in. I think some of these are just like outside the interval, because if they show up, since we're generating random numbers, there's a chance that nobody shows up. Like if someone shows up here, let's look at I just want to look at part ready. So it goes from 0 to 10,000, or sorry, 1,000. And then let's look at when people are arriving. Where did they arrive? People arrival. Oh, so we're only arriving halfway through. That's why. What am I doing? Zero to 1,000 seconds. Dot sort. So they're getting here from 0 to 1,000 seconds, and we're building parts much longer. Oh, because we have a lot more parts than people. Let's make 1,000 people show up to collect the 1,000 parts. Yeah, that's a little better. At least we're getting up a little bit higher. But it's still a lot lower. I feel like it should be closer. Anyway, we are getting that this distribution that we were trying to get of like, here is our measured, based on our experiments with folding paper airplanes, this is our measured like time, like how long will it take to get from one assembly to the next. Half the time it'll take 100 seconds. 100% of the time it should be less than 200 seconds. Always less than 300. And sure enough, like 90% of our customers are going to be in that 200 to 300 range, or less than 300. So most people will be less than 300 seconds. So that might even be like the upper bound for when we can say. And we want to add text. Let's get rid of this one. In this analysis, the difference between measured assembly times and customer wait times is simulated by building parts and how many? I think we made 1,000 parts. And average time difference of, and here I probably need like some of my data, right? Here, make a code. np.mean of time, one hand, np.standard deviation, time one hand, .5 seconds, and customers arrived at random times from 0 to people arrival dot min from 1 to 1,000 seconds. I guess I could do times n assemblies times np.mean of time one hand, if I want to take, because before I was assuming it was always 1 second intervals. That looks better. All right, so the main thing that I did there was, this is assuming that people are going to come every second to get an assembly from 0 to 1 seconds for every assembly that we complete. But I multiplied that by how long it takes to make one part, so the mean of that time one hand, and now I get a smoother curve. All right, so that looks better to me. At least maybe it looks better to you too. Hopefully it looks better. The main thing that looks better to me is that with 1,000 people, I was expecting less like staircase sort of things, like things happening, lots of people arriving all at once. Now it seems like we're getting just 1 or 2 people in each interval. Like it's kind of smoother increasing. It's that way. And now we can see like by 300 seconds, everyone always waited less than 300 seconds, but only half the people waited less than 120 seconds, even though what we would have predicted just based on our assembly times would be 100. The average, predicted assembly times would warrant 50% of assemblies or predicts 50% of assemblies will be finished in less than 100 seconds based upon the cumulative distribution of bus intervals of, let's change this, assembly times this is different from the weighted average of random customer arrivals, where 50% of customers will be in intervals of less than, so 50%, let's call this 130 seconds. And here I kind of skipped over the introduction of like how I was doing this and then the methods a little bit, but I wanted to get to how do I actually describe this discrepancy, because really you would, at least I would think these should be the same curves, that if I'm creating parts on average at this speed, customers should on average receive parts at this speed, but that's not the case. The case is that there's a definite shift, like a slowing down that is real. Like if you interview customers, the customers on average will report that they're waiting longer than what your factory is measuring for these times, and it's because you're waiting, like not W-A-I-T, but actual waiting on weighting it based on how big those time intervals are. And this happens kind of what we saw in this waiting for the bus. This happens for bus arrival times. It also happens in Alan Downey, I think, what was it? It wasn't ThinkStats. let's go to HackMD. And we're going to our reading discussion. Yeah, probably overthinking it. So this is also happening in like relay races, or if we look at like the distribution of class sizes. If you talk to other students in a university, they're going to report that on average they're in these huge classes, but the dean is going to report that on average classes are very small, and it's weighted based on, you're much more likely to talk to someone in a big class because it's a bigger class than someone who went to a class with 5 or 6 students in it. That only makes up 0.01% of our population. So if you interview every single person in the school, then maybe you would get to this curve. But if you're weighting it based on, if you're just looking at the numbers based on like how many people said 6 people versus how many people said 300, there are 300 people that said 300 and only 6 people that said 6. So you end up weighting that average. And so Dr. Downey, he goes through and actually looks at like how to create this from statistics. We're using some Monte Carlo to try to like simulate what's happening. Like, can we, so here's like Boston train. If you're waiting for the train, how long are you going to wait? And and this one was kind of cool. If you're looking at how many friends you have on Facebook, or so you could use it for any social media, like how many connections do you have on social media, is that in general, everyone you know has more friends than you. And yeah, and that one feels almost hurtful, right? Like that everyone you know knows more people than you, but it's a numbers thing again. Like the people that are well connected, you're more likely to be connected to. So it's not that you don't know as many people, it's that you're not as active, and therefore you won't have as many internet connection, like social media connections. And this one I like same thing happens with if you're driving or if you're running. It always feels like people are always going a lot faster or a lot slower. Like you're always passing people or you're always getting passed by people. And if you're a spectator just watching the race, you would see more of a normal distribution that, all right, well, most people are running 10 to 11 miles an hour or kilometers per hour, and there's some distribution, right? But when you're in the race, the only way that you could see somebody is if your speeds are different, and the bigger the speed difference, the more likely it is to see the person. So anyway, I wanted to kind of walk through this in like my own thought process, because it's kind of a weird thing. Like we're using some measurements that we actually took in class, some graphs where cumulative distribution, that can be kind of a weird thing to interpret and talk about. But the thing that I wanted to get at least in this assignment, like maybe you saw that there were other things that were more important other than, to me, this is the biggest difference of like what happens to your customer versus what's happening on your factory floor, because there's a big difference between your measured times and the actual experience of waiting for you to finish this stuff. And again, it's a little weird to try to talk about this, but that's what this class is for, is like trying to get these conversations as part of, and your get it part of your like thought process here. All right, anyway, rambled on for a while. Hopefully this helps, and I will catch you next time.